Otherwise, the thing will accelerate to the left and right. We can find out what the sum of everybody pushing in the right and left direction, just like we did a minute ago, by finding the components of these forces. First, we take a look at this force. This force has no horizontal component. Therefore, we don't enter him into this equation. Plus, since he's going to the right, the force in member CB times the cosine of the angle between the force and the direction we are discussing, 30 degrees, minus the force in member AC times the cosine of the angle between the force and the direction under discussion, 45 degrees. But we have one equation with two unknowns, and therefore we're going to have to get another equation in order to solve for it. Second equation says that the sum of all the forces up and down, if this is not a rocket, it's not, is 0, is equal to. We subtract the 98.1 newtons, that's 10 times 9.81. We add FAC, but not all of FAC points up, just a piece of FAC points up. So we multiply it times the cosine of the included angle. And then also pointing up, and therefore called a plus, is FCB, multiplied times the cosine of 60 degrees is the angle between the force and the angle and the axis direction under consideration. And then all you do is you punch it in the calculator and you solve those two numbers to tell you the answer for the force in CB and the force in AC. Alright, now then, since they have three-dimensional information in the text, that makes it possible that they may give you some three-dimensional problems on the quiz. These work in exactly the same fashion as a two-dimensional one that we just worked. When you get to 3 dimensions, it is normally the case that you will keep track of the guy's X, Y, and Z projection along an axis by tagging the individual X component with what they call a unit vector, I. And it's not at all difficult. All it is a tag, a name, an identifier that says I goes with the x-axis. It's just a reminder of who we're discussing at that time. I is considered to have a unit length of 1, and therefore when multiplied by the 10, you don't mess up the fact that this guy points 10 in the x direction. And incidentally, the minus sign means that he points in the negative I, or the negative x direction. As you see, he does. He's pointing to the left along the x-axis. He also has a component 40 in the j direction. That's 40 in the y direction. And it is going up, and 50 in the z direction, or 50 in the k direction. And that defines this force, this vector. The nice thing about keeping track of the components of the force in this fashion is they're very easy to add. Because if you would like to know one resulting force which would replace all 3 of these guys, all you got to do is come take this x component, add it to this x component, add it to this x component, and you have the x component of the resulting force. So for example, the one resulting force that would resolve these 3 forces would be minus 10 plus 15, we're 5 ahead of the game so far, plus 20, so that's plus 25 with an I for an identifier about which way we're talking about. And incidentally, in your notes or in your book we gave you, you'll see there are three answers. One of them is perhaps the force is this. And then over on the other page he has another R with some different numbers written down. And then he has another one with some more numbers written down. The truth is, this is really easy to work. If you look at the other ones, this one says, I forget what it says, but it says something like 17I, and this one says minus 23I or something like that. Then there's probably one, if you were taking a real quiz, there's usually 5 choices. One of them says 22I. Well, none of these got a chance of being the answer. If you look in your book, you see this is the only one's got a chance of being an answer, because it's the only one that has 25 in front of the X direction. None of the others have any chance, because 10 to the left plus 15 to the right plus 20 to the right along the X-axis doesn't equal any of these numbers. No way, no way, no way. This is the answer. That time you mark I on the quiz and you go on to the next problem. Alright, sometimes you will see a force, instead of already being broken up into the X, Y, and Z components, you may see the force comes out here at some angle, and they tell you that this force came to here, and to here, and to here. In other words, it's sitting at some dimension. Perhaps this is 10 meters, this is 8 meters off of the X-axis, and this is up in the air along the Y-axis 20 meters. A lot of times, rather than showing you where it is to the end of the vector, they'll just show you from this point on the vector to another point on the vector. In that case, they may go over, and then they come out, I'm not sure, and then they should go up, and they show it like that. And they may show this is a 10, 8, 20. But regardless of how they do that, if this was a 200 Newton force, you would be asked to be able to find this force's projection on this axis. You would have to be able to find this force's projection on the Z-axis. And you would have to be able to find this force's projection on the Y-axis. And that's pretty easy to do. It works just like it does in a two-dimensional case. First thing, in a two-dimensional case, you and I found out how long the vector really was by taking this squared, that squared, taking a square root. You can do the same thing with this original vector. This original vector has length 10 squared plus 8 squared plus 20 squared, and then you take a square root. So that says any vector sitting at that position in space has a length of 23.7 meters long, or whatever our units are. Now that means that this guy right here would be the force along the X-axis, and the force along the X-axis would have the magnitude 200 newtons, except not all of this points in the pure X direction, only 10/23 of it. That's how you find the X component, by saying how much does he point down the X-axis. He points 10 out of his total length of 23.7, and that's equal to 84.4 newtons magnitude along this three-dimensional X-axis. So that says this guy right here would be 200 newtons, and you multiply him times 8, because that's how much projection he has down that axis, over 23.7. Tells you he points in the z direction a total of 67.5 newtons. And this guy right here points up 200 newtons multiplied times his upward projection was 20 times 20 over 23.7 is equal to
168.8.
168.8 newtons. Then if you take 168.8, square it, plus 67.5 and square it, plus 84.4 and square it, you ought to come out with, and hit the square root button when you add those three together, you ought to come out with about 200 newtons. And if it doesn't, then you just got a mistake in there. You'll have to dig it out. So that's how you find out a three-dimensional force's projection upon axes. Alright. Now then, let's talk about a second action or behavior. Forces not only have the tendency to push refrigerators to the right, they not only have the tendency to pick things up in the air, they also have a tendency to rotate those things. Now, many times the item itself is never truly going to rotate. It's really tied down tight. So instead, we may say, how much moment is there about a point, or how much tendency to rotate is there about a point? For instance, this 500-pound force's tendency to roll about point A can be found by two items. First, we'd call it a moment. It is the moment of the 500-pound force tending to roll about point A. It doesn't really roll about point A, but it tends to. If it were to get away from us, it probably would. You get the magnitude of that moment by multiplying the magnitude of the force. The bigger the force, then obviously the bigger the moment, times how far is it? How far is it from point A? Well, it's obviously 5 feet from A, for a total of 2,500 foot-pounds of moment, tendency to roll. Now you also need a sign convention. Most people pick this as positive X. Most people pick up as positive Y. And right-hand rule is easy to remember because that's the way your right hand is made. But a lot of people may pick the other direction. If you have, no problem. But just for grins, I'll pick that as the sign convention. I'd write it down so everybody would know, and then I would put a positive in there. The reason is if you'll bring this force to point D, tie a string to it. The length of that string is what they call the moment arm. Then once the string is tied on nice and tight, let the 500-pound force go. He goes to the left, but because the string is tied to him, he will start to roll about point A in this direction. That is a tendency to roll the way our hand is made, the right hand, and therefore it is tagged with a positive tendency to roll. Alright, now let's find how much bending moment there is of the 500-pound force about point C. Here's the force. Here now is the point that I want to know how much tendency there is to roll. Now the moment arm is actually the perpendicular distance from the line of action of the force. It is not, for instance, just because the force is tied here, this is not the moment arm. This is the moment arm for this 500-pound force. If you have trouble with that, what you do is you get on this 500-pound force, you follow it to infinity in both directions, and when it gets as close to point C as it's ever going to get, stop moving your pencil. So here's the force. I start moving the force to the right. This is as close as it's ever going to get to point C, and therefore I tie the string to the force right there. The length of the string that I tie is 5 feet. It's a 5-foot string, and therefore the moment of the 500-pound force about point C is equal to, first you take the magnitude of the force, then you multiply it times the moment arm, and we get the same thing as we got before. Now sometimes your forces will be sloped, and the guy will ask you for the bending moment about point C. So here is the bending moment for the 2,000-pound force about point C. Well, strictly speaking, you should follow the 2,000-pound force to infinity in both directions until you get as close as you ever intend to or are able to point C, and it looks like that's the moment arm right there. Well, fool me on trying to figure that number out, as I've forgotten the equation to determine the distance between a point and a perpendicular to a line. It's a lot easier to take the 2,000-pound force's horizontal component and the 2,000-pound force's vertical component and find their tendency to rotate about point C, which is identical to the original force's tendency to roll. So this horizontal force right here would be 2,000 pounds times the cosine of 30 degrees. How much is that?
1732.
1732. And this vertical force is 2,000 pounds times the cosine of 60 degrees. 1,000 pounds. So now we can find the 2,000-pound force's moment about C by multiplying first the 1,732-pound force times his own personal moment arm. Well, here he is acting horizontally through D. He will get this close and no closer. He'll get to point B. If you tie a string to him at that point, that string will be 5 feet long, so he has a 5-foot moment arm. His tendency to roll, if he gets to point B and is tied to a string, he will roll this way, and therefore that is not a positive moment. It is a negative tendency to roll. Then we take the 1,000-pound force at D, the second component of the 2,000-pound force. We have 1,000 pounds of force. We have a moment arm. A lot of people, and I can almost assure you one of the answers on the quiz would be that the moment arm is from here to here. Another one probably is that the moment arm is from here to here. But the truth is, here's your 1,000-pound force. You're supposed to follow that 1,000-pound force until it gets as close to point C as it's ever going to get as close as it's ever going to get as close as you went too far. That's it. That's the moment arm. How long the string would be to tie to that force is 2 feet. A 2-foot moment arm. So you multiply that times 2 feet. Now, the tendency of this force to roll, pull it back till it gets to where you can tie a string to it, tie the string to it, and then let it go. Since it's pointing up, it'll start rolling this way about point C. That is not a positive right-hand rule moment, so that term is also minus. And then it doesn't matter what you get, but whatever you get is the sum of those two numbers. Now, sometimes you have structures that are three-dimensional. In this case, I have a piece of pipe which is 15 centimeters tall. Another piece of pipe is welded to it, 10 centimeters big, long. A 200 Newton force sitting at an angle of 20 degrees. Before you can find any moments inside of this thing, without a doubt it's going to be to your advantage to find out the vertical and horizontal components of this 2,000-pound force. The horizontal component would be 200 cosine of 20 degrees, also equal to
187.9.
188 pounds, newtons. And the vertical component would be 200 newtons times the cosine of 70 degrees for an upward component of
68.4.
68.4 newtons. Alright. Now here about all you can do is just carefully look and see who is tending to roll around a point or a line. The problem that probably would be asked on this quiz would be how much moment is there about the x-axis caused by anybody out there. I don't care who it is. You need to remember that this force, the 180 Newton force, is parallel to the x-axis and therefore causes no tendency to roll about that axis. This force, however, is perpendicular to that axis, and therefore, being 10 centimeters away, it would cause some tendency to roll about the x-axis. That moment would be 68.4 newtons. You would multiply it times how far this is away from the x-axis. That's 10 centimeters. So 684 Newton centimeters. Most people probably call that a Newton meter, and move the decimal down to be 0.684 Newton meters worth of moment, worth of tendency to roll about the x-axis. Next, how much tendency to roll is there about the z-axis? Well, about the z-axis, this 68 Newton force is parallel to the z-axis, so it has no tendency to roll around that axis. However, the 188 Newton force is perpendicular to the z-axis. You can see it would roll around that axis, and therefore it is equal to 188 newtons multiplied times how far it is off of the z-axis, 10 centimeters, and whatever you get. So that'd be like a three-dimensional problem with moments. Alright. Another force may act on a cable as opposed to something that is a little more rigid, like a piece of steel, and in that case the forces would cause the cable to sag. If the cable is relatively light, as you will be able to assume on this quiz, then it would deform the cable into a series of straight lines. Now, where point B and point C and point D would be depend on two things. They depend on how much force you apply to the cable, and also how long the original cable is. As you might imagine, if this guy up here at E fed in another 30 feet of cable, all of these points would drop down. So you will have to be given one of these elevations. You'll have to be able to know how far it is with reference to A and with reference to E. They'll also have to tell you how high E is above A. But one of these will have to be known in order to solve the problem, otherwise you can't solve the problem. Now, this set of forces causes a pull on A, and that pull on A is directed along the axis of AB. But again, to make our life easy, we can break this force into two components: an A horizontal component and an A vertical component. In that case, there's really not much question which way they go. Since the cable is pulling down and to the right, the reaction will have to resist up and to the left. But there are two unknowns, and we do not know their magnitudes. You can, however, go over here to joint E and sum moments about that point. Here would be your equation. Sum moments about point E is equal to 0 if the whole cable is not collapsing, and it's not, it's just sitting there, is equal to, first you see a 4-kip load. Follow him until he gets as close to point E as he's ever going to get. He's 15 feet away, so his moment arm is 15 feet. And his tendency, once you tie this 15-foot piece of string to the force, you let it go, it would tend to roll this way, tied to the string, and that is a positive tendency to roll, so that's a positive moment. Plus, then the next one would be 12 kips times his moment arm. He's 30 feet away. Next, there's a 6-kip force, and he is 40 feet away. Next, there is an A vertical force, and he is 10, 20, 30, 40, 50, 60 feet away. And as you notice, if he were to get away from you, tied to a string, he would tend to start rolling this way, and therefore he has a negative tendency to roll. And then finally is this A horizontal force. Again, follow the A horizontal force until it gets as close to the point you're summing moments about as it's ever going to get. That's too far. That's just right. Can't get any closer than that. Your moment arm is 20 feet. So A horizontal times a 20-foot moment arm, and his tendency to roll, drag him back here, drag him back, stop right there, put him on the page and tie a piece of string to him. If he gets away from you now that the string is attached, he'll roll this way. That is a negative tendency to roll, so you put a minus. Now that gives you one equation, but unfortunately it has two unknowns inside of it. So we must find another free body to give you a second opinion about what these two forces are. You could sum moments about B, but you don't know the moment arm because you don't know how far this B point sags down. So here's a good point to sum moments, because I know where C is horizontally, and someone measured how far point C was below this reference line. So the second equation says sum moments about C. Now this is your free body now. Your free body now includes only this left-hand piece. So I could take a piece of paper and completely cover that up, because you don't even know that side exists. There's nothing over there that you can use in order to keep this free body in equilibrium. Alright, we say the sum of the moments about C is equal to 0 is equal to, first I see a 6-kip load. He is 10 feet away. Were he to get away from me about point C, he would roll this way. That is a positive tendency to roll, so I put a plus in front of that moment. Minus, because of the way he's going to roll, A vertical times 30 feet minus A Let's see. A horizontal. Here's A horizontal. Let me put A horizontal down first. A horizontal. His moment arm, he is 5 feet away. So the moment arm is 5 feet. Now let me see which way he's going to roll. I drag him back here.